In this video, we will study permutation with identical items and without replacement of n objects taken n-2 at a time, and we will derive the formula expressing that. So let's start with the following question. How many distinct 12-letter words can be formed from 2 A's, 3 B's, 4 C's and 5 D's in order and without replacement? So we have the following word here, and we have 2 identical A's and 3 identical B's and 4 identical C's and 5 identical D's, and the sum of all these letters is n equal to 14. So we have 14 letters of this sequence we are starting from. So now to compute the number of 12-letter words out of this 14-letter words, we have to reduce it by 2 letters. So what do? We can take letter A off and B off. So we take A and B and we get this word with 12 letters, or we can take letter A off and C off and we get this 12-letter word. We can take A and D off and we get this 12-letter word. We can take B and C to get the 12-letter word. We can take B and D to get also 12-letter word. And finally, we can take letter C and D to get this 12-letter word. And now we have 6 words resulting from taking 2 different letters off from the 14-letter word in order to generate 12-letter word. So we take them back a bit and up a bit, and now we write the corresponding permutation for each word. But at this time we will replace these numbers with their corresponding symbols as we see here. So we replace 2 with A, 3 with B, 4 with C, 5 with D and 14 with N, and we get this formula here. So we repeat that for each word and we get all these formulas, and now we have to add them up. So we add all these formulas together and we call them P1, and the reason why is because there will be another set of words coming later. So we replace every A minus 1 factorial by A factorial divided by A, and we do that also for B minus 1 factorial, C minus 1 factorials and D minus 1 factorial. So we substitute that in the sum of permutation formula, and we can see now the substitution here for A and for B and for C and for D, and we add them together and we get this formula of P1 here. Now to compute the number of 12-letter words out of this 14-letter word, we can take 2 A's off. So we take 2 A's here and we get this 12-letter word, or we can take 2 B's off to get a 12-letter word, or we can take 2 C's off and we get this 12-letter word, or we can get 2 D's off and we get this 12-letter word. So now we have these 4 words. We take them back a bit and now we write the corresponding permutation of each word. But at this time we will replace each number with its corresponding symbol. So we replace 2 with A, 3 with B and so on, and we write the corresponding formula now. And that is for the first word. We repeat that for the second word and the third and the fourth. And now we have 4 formulas and we can add them together. So we add them And we remember that a factorial is equal to a times a minus 1 times a minus 2 factorial. So that means a minus 2 factorial is equal to a factorial divided by a times a minus 1. And the same thing is applicable for b minus 2 factorial, c minus 2 factorials, and d minus 2 factorial. So now we can replace each a minus 2 factorials with this term here, and the same for b and c and d. So this sum we are going to call P2, and we replace a minus 2 factorial with its corresponding term, and we do that for the rest. And now we rearrange again, and we get this formula. Now we can expand and write it in this formula. So P2 is equal to this formula, and now we have to add P1 plus P2 in order to get the total permutation for this 12-letter word in theory. So the permutation formula is equal to the formula of P1 plus P2, and we replace that, and we have the same denominator, so we add the numerator and we rearrange, and we notice that a plus b plus c is equal to n. So we replace that with n, and we get this formula here. Now we have to deal with the sum of these squares. So we start with the square of this sum here, and we expand it, and we notice that a plus b plus c is n. So we replace that with n, and now we can write that the sum of these squares is equal to n squared minus these terms. So we have this formula, and we have the sum of these squares, so we replace the sum of these squares with these terms here, and we get this big formula here. So we rearrange it again, and we notice that n squared minus n can be factorized into n times n minus 1, and now we can write this formula into two fractions, but we notice that n times n minus 1 times n minus 2 factorial is n factorial. And now we arrive at this formula here. So this is the formula we are seeking, and we can read it as permutation of n objects taken n minus 2 at a time without replacement with these identical items a, b, c, and d. So now we can apply it on this. So we have 14-letter words, and we need to compose 12-letter words. So that's why we have here n minus 2. So we replace each a with 2 and b with 3 and so on, and we get these numerical fractions, and the final answer is 1,538,460. We have second question here. How many distinct 11-letter words can be formed from these letters? 1 A's, 3 B's, 4 C's, and 5 D's in order. So we have 1 A, 3 B's, 4 C's, and 5 D's. And the total number of these letters is n equal to 13. So we want to compose 11-letter words. So this word is n minus 2 out of this n-letter word. So we have a equal to 1, b equal to 3, c equal to 4, d equal to 5, and n equal to 13. And now we have to substitute in the formula. So now we substitute in the general formula these variables here, and we get permutation of 13 objects or 13 letters taken 11 at a time without replacement with 1, 3, 4 and 5 identical letters, and that is going to be 224,070. And now we have very simple question: how many distinct two-letter words can be formed from two A's and two B's only, in order and without replacement, of course? So we have two A's and two B's, and the total is 4. So we have these variables. Now we are going to substitute in the mother formula. So we substitute that in the permutation formula of n taken n minus 2 at a time, and we have permutation of 4 letters taken 4 minus 2 at a time, which is 2, without replacement for these identical items, and we realize that the last two identical items can be substituted by 0. So we get 6 minus 2, and that is equal to 4. We can verify this answer that we have 4 words we can generate by invoking the original words. So this is 4-letter words, and we want to generate 2-letter words out of it. So we can have AB, BA, AA, or BB. So these words are written in order, and they are really 4 words that can be generated, and that's exactly the answer we got here, which is 4. So we have simpler question here, number 4. How many distinct one-letter words can be formed from one A and two B's in order and without replacement? So we have 1 letter of A, 2 letters of B, and the total is 3 letters, and we want to find how many one-letter word we can compose out of it using that formula in order to verify it. So these are the variables, and now we have to replace them in this mother formula here. So we have permutation of 3 letters taken 3 minus 2 at a time, which is 1, without replacement for these identical items. We don't have C and D, so we replace them with 0, and we get 3 minus 1, and that is equal to 2. So we can see that this is the mother word ABB. We want to generate 1-letter word out of it, so we have either A or B, so this is 2, and the formula even works for the simplest example. We can generalize this formula for more identical items. So let's say we have A, B, C, D, and E as an extra one. So this is the formula we can write now, and a permutation of n objects taken n minus 2 at a time, without replacement for these identical items, and we can realize that we number A as the first variable multiplied by the sum of the rest of the variables, plus B, we regard B as the second variable multiplied by the remaining sum, and C as the fourth variable multiplied by the rest of the sum, and D as the fifth multiplied by the remaining variable, which is E. So this way we can apply this formula for more and more identical items. Thank you for watching, and have a good day.